Welcome to Brain Vision.
In this problem, we have a beam that has a what they've drawn it to have two distributed loads on it. One that is linearly varying in the negative y direction, and one that is positive, that's uniform in the y direction. We can actually combine these two because they're just sum up, and what we get is actually a distributed load that looks like this, which is 0 in the middle, has a value of minus 3 kilonewtons per meter at the left end, and has a value of 3 kilonewtons per meter at the left end, and minus 3 kilonewtons per meter at the right end. So this function has a slope of so it goes like 2x. Okay? And we have a constant of integration would actually be just 3. Right? So it'd be 2x plus 3 is how, well, actually no, because again, they always draw these things, it's always kind of confusing, but these are negative values, so this would actually, let me actually just write this out. W of x is going to be 3 minus 2x, because it's positive value of 3 here and negative value of 3 here, 0 in the middle at x equals 1.5 meters. So if we just look at this, we can then get our shear. Well, we can find our bending moment. We can note first that the distributed load, the equivalent point load, is actually, or the magnitude of the distributed load is 0. So we don't, we have the shear, the reaction force at the clamped end here is 0, because basically these cancel out. So we have no, the moments, however, we have, again, we can make an equivalent point load here and an equivalent point load here. They have the same magnitude, but they'll create a couple that needs to be overcome by the reaction at the wall here. It turns out that moment is minus 4.5 kilonewton meters. To get the shear, we can integrate this and then find the constant of integration. The constant of integration is actually going to be 0 because we know the shear stress is 0 when x equals 0. And so our function for the shear force throughout the region is x times the quantity x minus 3. So we just have this parabola here. Then we have the, let's see here. I think I forgot to put a minus sign in here. Yeah, I did. So let's see here. Then we have, we can then integrate this to find the function for the moment. And then we know the moment out here at x equals 3 is 0, so we could find the constant of integration. So if we integrate this, find the constant of integration, do some manipulating of the function, what we wind up with is minus 1/6 times the quantity x minus 3 squared times 3 plus 2x. And we can see that, again, so when x equals 0, we're at minus 4.5 kilonewtons per meter. Okay, so if we use this point to find our constant of integration, then a good check would be to make sure that at 0 we get back to this value. We can see that at x equals 3, again it's m is 0 as we'd expect out here, and it's a cubic function that then basically has a negative, a positive curvature and then a negative curvature. And we can see it reaches a maximum and a minimum at the ends when the shear force is 0. And then there's an inflection point here where the shear force is a maximum.